Perfect.
Okay. Hello, everyone. My name is Akram. I'm from the AI4Good lab in Nairobi, Kenya, working with Girmao and Caleb. I wanted to go over the current project that is still actually ongoing with our partners, the Kenya Wildlife Trust and Smithsonian Institute. So what we're trying to do here is to first start to tackle the problem of wildlife conflict resolution by using AI to first map boma and cattle distribution in the Masai Mara. So to motivate the project, as we know, the Masai Mara population, as it continues to expand, the incidence of conflicts between the settlers and predators continue to rise. This looks like the figure you see at the center. So we have these weakly fenced bomas. They get attacked by predators that cause loss to the people, which they retaliate in turn. We know that this is a multifaceted problem. Our approach is to just start with the basic things. We just want to first map the spatial distribution of bomas. Where are the bomas settlements located in the region? And subsequently, once we create a quality data set, we can actually create derived data sets and know where the hotspots of conflicts are, and then route resources necessarily. So our contribution here is to just start by using AI and high-resolution satellite imagery to automate the process of identifying where boma settlements are located. So to give some context, we start with a single satellite image comprised of two scenes and a few labels. However, the labels were point labels, and we wanted to do segmentation, meaning we wanted to also map the areas of the bomas or the entirety of the geometries of the bomas. So we used previous data set to guide the process of a new labeling approach, right? So we can break the problem into two steps. First, we want to find the boma settlements. This is, in computer vision terms, a segmentation problem where you want to map or detect the exact geometries of the bomas on ground, and also the buildings or the structures that surround the bomas typically. That's the first step. Second task is to have some signal of how active a boma is, or is it active or not? Meaning, at the time of the image being captured, was the boma populated? Did it contain cattle or not? So typically the process we did is we start with the image, we use the point labels, we annotate or label a few boma geometries and train a model, and then use that model's outputs as feedback to add more labels. Now, the labels can be positives, meaning more bomas to be added to the training data set, or negatives, where the model is getting confused and maybe it's producing too many false positives, and we need to tell it explicitly that these set of pixels don't actually contain bomas. So that's the iterative process you see on the right figure. An overview over the data set. So as I mentioned, this is we consider a single image. It's comprised of two scenes from World View 2. It covers 3,600 square kilometers. It is the region or the rectangle in blue you see on the map. While in the middle, you can see the point labels from Land DX in yellow. And those were actually the guiding they guided that through adding our own labels on top. It consists of 4 bands, so RGB, near, and panchromatic band, 50 centimeter spatial resolution, and it is captured in a single day in the morning. So as you see on the far right image, you can see the satellite image, and overlaid on top of it some of the labels that we created. In green, the bomas, And then in red, if you can see the very small rectangles, these represent the structures. So we took this image and we actually manually added a few labels, starting below 100 and then incrementally adding more and more labels to make the model better. So to summarize, it's a single image. We do some manual labeling ourselves. We use the model to guide further labeling that is most useful to learning, and converge to hopefully a satisfactory performance. So that was the first task, right? Like we needed to create these polygons for the BOMAs, but then we still need to do the classification task, which is about cattle presence. Is there a cattle inside the BOMA in the morning? And that is overlaid on top of the first data set. So what we wanted to, or what we did, is that we just took the polygons, we created patches, and then we label or tag these patches as either 1, meaning populated on the top row on the left figure, or empty, and that's 0, right? So that's the second level of annotation that was useful for the second task, which is cattle presence. So in essence, we have 2 data sets that are intertwined. And what we did after that is simply try out many architectures, computer vision for segmentation and classification to get a performance that is good to start with. So the numbers you see there are expressed in F1 score as F1 scores, pixel-wise F1 scores. And we get in, around 0.8 F1, which is decent. Classification is much better because it's kind of a simpler task. You're not really doing segmentation and want to get every pixel correct. You just want to classify the whole patch. And I want to note here that the biggest challenge really was about the data and the labeling process, right? So we started with no polygon labels, and we really had to be strategic in the way we label, where we label, and to really reach our goal. And one other thing I would add is that there's always domain shift problems. In simpler terms, if you train the model in one region and you want to take it to another region, because of the great variability in the image, the model would just break, right? It would break in some new patterns that it never saw in the training region, or in clouds, or in other, in general, just new patterns in the image. So we had to continue even scale to other regions, pick labels from other regions, which resulted in 3 splits, actually, 3 training validation region splits across the whole scene. Another technique that we tried that has to do with solving this low label problem is that we wanted to make the model kind of more conservative, because it was producing a lot of false positives. The reason it was producing false positives is that most pixels don't really correspond to either BOMA or structure, and we weren't sure that everything else is negative, of course, because there can always be BOMAs elsewhere. So we just ignored most of the pixels, and that made the model just, for example, predict positives there and not being penalized by the loss function. So what we did to solve this is to just base it off an observation that for these false positives, the model wasn't sure. So the probabilities were kind of equal, meaning there was high entropy. And that motivated us to add an entropy term to the loss function. That's the second term you see in the equation, h of y hat. And that really tells the model or directs or enforce the model to only predict positives if it's quite sure about them being positive. Otherwise, it would just cancel to or collapse to the negative class. This really showed some improvements, especially in the low label setup, when you have like less than 100 BOMAs or below certain thresholds for negatives too. That was useful too. The goal really was to produce an AI dataset and continue to work on it and improve it. Based on a model that was actually showcased in this slide, kind of outdated, but it produced a. So what we do just to give context is that once we train in over a region and we validate the model, we can just take that model and run it through the whole 2 scenes or the whole image, and then produce the final data set that we want. And in this case, we have the model being able to detect around 5,000 empty bomas, 160 populated bomas, and around 20,000 structures. What we did too is that we did some post-processing because the model just predicting pixels and we want to vectorize. So we did geometry simplification, for example. We removed outliers manually or by distribution thresholds and other kinds of techniques to smoothen out the geometries. And the message here is to just like show that maybe you can start with a few labels or no labels, and take a model and fine tune it and be able to map a big region. So this is an example of that model snapshot predicting. So on the left side, you see the input, and you can see some bomas and some rooftops that are distinguishable. And on the right side, you can see the same input and the overlaid predictions by the model of the exact BOMA boundaries and structures, right? The BOMAs are in green, while the structures are in red. So this is one example. This is a second one. Some of the structures, by the way, they're very small that you can't really see them. But if I zoom out, they will be more apparent. Again, here, what sometimes the model makes mistakes is it doesn't really map the exact boundaries of the bomas. It would sometimes also only detect a sub-region or a sub-area of the boma, meaning that it's more biased towards color than boundaries. And this is one thing that we want to tackle next. Here's a final example. Again, like the richness of it, there are many buildings or structures there and bomas, and the model is doing fine at mapping at least the locations of the bomas and buildings. So what we want to do next is, again, this model was trained on a single, although huge region, but it's a single region that doesn't cover the whole Mara. So we want to scale the model to other regions, and that requires acquisition of other images, and also scale it temporarily and test the model performance on other timestamps, and hopefully create a quality data set that not only shows the locations of the bomas, it can accurately estimate the areas of the bomas, and inform analysis on top of, and through time, of course. So it will be a spatio-temporal data set. The second thing we want to do is to, again, tackle this issue of capturing boundaries that would result in better estimates of the areas. Of course, essential is to do ground truthing of the model. Again, the labels were created based on visual inspection, and manually, they were just manually created by just looking at the image. But we want to ideally task imagery in the future and collaborate with our partners to do some actual ground truthing of the model and finally publish the data set. So the conclusion is that we can really use AI to map BOMA structures in the Masai Mara on a huge scale. We were able to cover very quickly many BOMA settlements. The impact, as you know, more than myself, is to help our partner like direct resources better in predator conservation, mitigation of human-wildlife conflict, and of course continue to support open dataset initiatives and AI by publicly publishing our workflows, our AI model weights, and the datasets resulting from the model. And that's it. Thank you. Back to you.